Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you to this session. This week we are revising properties of matter. Okay, we already had yesterday lecture um, about viscosity. Okay, in that lecture we learned about the linear velocity profile and some problems of non-linear velocity profile as well. We will continue this discussion in today's lecture. Okay. So without losing any further time, let's share our screen. So here we go. So let's have a recap of previous class a little bit. So you understand that when there is relative motion between adjacent layer of fluid, okay, they try to oppose the relative motion between them by exerting a tangential viscous force on the surface, and the expression for that viscous force is given by this. F is equal to minus eta times A dV by dy. Okay, so we must realize that this viscous force, okay, is directly proportional to area, directly proportional to this velocity gradient, and the proportionality constant here would be eta, which is nothing but viscosity of fluid, or you can also say that is coefficient of viscosity for the given fluid. That will be depending upon the nature of fluid we discussed in yesterday's class. What I want you to be noticing over here, first of all, two things which we discussed through problems in yesterday's class. First of all, F in will be in tangential direction or tangential to surface, okay, and it will be directed opposite of dv by dy, like that is what this negative sign means over here. And the secondly, you must realize, like, net force acting on a thin layer of liquid should be equal to 0. In steady state, you can say, means the velocity profile has been set up and the velocity of any layer is no longer changing with respect to time, so that will be moving with uniform velocity. So the net force acting on a thin layer of liquid should be equal to 0 in steady state, we must say. Okay, so carrying these ideas into the other problems which we are going to discuss. Okay, so let's have one of those problems. Let's say we have two coaxial horizontal tubes. Okay, coaxial means they are having their axis coinciding with each other. So let's say we have two coaxial tubes. Okay, and the radius of inner one is r1 and the radius of outer one is r2, and there is liquid filled between these two coaxial cylinders or coaxial tubes, you can say. Okay, so what we have to do here now, let's say the viscosity, this liquid is viscous liquid. Okay, so viscosity of this liquid here is eta. Okay, so now the cylinder is moved towards right with some constant velocity, say u. Okay, so you need to apply some external force on this inner cylinder, okay, in order to move this with constant velocity u. So here our problem statement is, first part is, what will be the magnitude of external force. F external we want to find out. And the second thing, like, what will be the velocity profile? What will be the velocity profile? For example, we want velocity as function of r, okay, where r is the distance of any thin layer of liquid from the axis of this tube. Okay, so we want to answer these questions. Okay, so how are we going to deal with this? So now uh, let's try to analyze. So imagine a thin layer of liquid. Okay, imagine a thin layer of liquid which is located at distance r from the axis. Okay, so the thickness of this thin layer, you can say, that would be equal to dr. Here you can see, so that will be forming, this small thickness will be forming a thin hollow cylinder, and this is what the element we are looking at, okay, over which we have to find out the viscous force. Now you must realize here, first of all, about the velocities. So you must realize, so this layer of the liquid is moving with the cylinder, so its velocity will be u, and this outermost layer of the liquid, since it is in contact with the outermost cylinder which is a stationary, so this layer of liquid will not be moving at all. So when you will be looking at how the velocity is varying, you must realize, like, as we go away from the axis, the velocity is decreasing. So for example, at this layer, if the velocity is v, so to the next layer the velocity v plus dv got to be negative, because the velocity is decreasing over here. Okay, so the velocity is decreasing, so you can say this thin layer of the liquid, the force it would be experiencing from the bottom, from the lower side and the upper side. So the lower side of the liquid is moving faster, so it will drag this layer by some force F. Okay, so the upper layer will experience something F plus df in backward direction. Okay, so this is the thing, and you should also realize that df got to be equal to 0. Okay, and also you must say, if we take a very small layer adjacent to this inner cylinder, that you must understand that this cylinder will be exerting a force F in forward direction. Okay, so the liquid will be exerting force F on the cylinder in backward direction. Okay, and all the magnitude of all these forces which we have drawn, represented this a red arrow, is basically equal to F. So this cylinder is experiencing a force F, okay, due to the liquid in backward direction over here. So that is why, in order to move this with constant velocity, we need to apply this external force in forward direction. Okay, so for the answer for the first part, that F external's magnitude would be same as this F over here, and that is the viscous force, and we are still required to find out the magnitude of this force F. As we know that this is viscous force, and the expression for F is given by minus eta into A into velocity gradient. So like the area which we are looking at here, let's say the length of this cylinder is L. So F is equal to eta, and the area of this cylinder, surface area of this cylinder, which we have taken as element, would be eta into 2 pi r L, okay, into dv by dr. Please notice we are looking at the magnitude of force. Okay, so this quantity here is positive, you see, because see, this quantity is negative and this is negative, so negative negative ultimately becomes positive. So this is the expression for force, and we want to find out the force using the uh, using the end conditions over here. So like this here is a differential equation. Okay, and we can rearrange this differential equation. That would be f into dr by r is equal to minus 2 pi eta L into dv over here. And please be advised that this force here is constant, like we already said. Okay, like f will not be a function of r, because any layer of this liquid is moving with uniform velocity, so force got to be constant. And now we must integrate with appropriate limits. Let's say we are integrating all these terms which we have taken outside of the integration signs are constant. So for example, at r is equal to r1, you can say the velocity of the liquid layer is nothing but u, and r is equal to r2, the velocity of liquid layer is equal to 0. So when we will be substituting these values, what we will be getting is f into ln r2 by r1 is equal to 2 pi eta Lu. So this gives us the magnitude of this force F. That would be 2 pi eta Lu divided by ln r2 by r1 over here. So the first part of this question we are able to solve. Okay, so the next part of the question asks for the velocity profile. The next part asks for the velocity profile. So let's try to find out the velocity profile over here. So again, looking at the same differential equation, dv uh, uh, will be equal to minus f divided by 2 pi eta L into dr by r, and we are integrating with appropriate limits. Okay, so we know that at r is equal to r2, the velocity is 0. You could have chosen the other extreme also, that r is equal to r1, the velocity is equal to u, but I think this would be more convenient for us. Okay, because it involves 0, and at r is equal to r, we want velocity as a function of r, so we need to integrate this. And in the previous part of question, we have already found out the value of this force over here. So when we will be substituting and integrating, like this v we will be getting is equal to f by 2 pi eta L will be nothing but u divided by this quantity here would be u divided by ln r2 by r1 over here, and this quantity here, taking care of this negative sign also, will become ln r2 by r. So now you see, so this is the velocity profile, okay, which is function of r over here. So that is the answer for the second part as well. Okay, so here you can see, like velocity is here directly proportional to like 1 by ln r2 by r, something like that. So that is a complicated profile here. Okay, so anyways, like we were required to find out this expression which we have got. Okay, so now let's move on to the next problem. Next problem here will be of non-linear velocity profile as well. So let's look at the question. So the question is, say we have two coaxial thin cylinders, and these are cylinders, two coaxial thin cylinders, and the radius of say inner cylinder is r, and the radius of the outer cylinder is 2r, and the liquid is filled between them, whose viscosity is eta. Okay, so now you see the length of the cylinder, let's say, is equal to L. Length of the cylinder given is L. So now what we are doing here, we are rotating these cylinders by applying some external torque. So that this inner cylinder, we are rotating with say angular velocity omega naught about this axis, and the outer cylinder we are rotating with angular velocity omega naught, but only in opposite direction. So now, due to the motion of this inner cylinder and outer cylinder, the liquid which is contained between them will also be moving, and different layers will be having a relative motion with respect to each other. So the adjacent layer will apply tangential force over each other, and that is why they will exert torque on each other, which will like basically set up a angular velocity profile over here. So in this question, what we need to find out, like the first thing we need to find out is, first of all, find the torque. Okay, like torque experienced by each layer, or that will be same as, you must realize, like torque experienced by inner cylinder as well as outer cylinder due to liquid. So equal and opposite external torque we need to apply on any of the inner or outer cylinder. So that is the first thing we need to find out. And the second thing we need to find out is like the angular velocity profile, omega as function of r. And thirdly, like for example, once we have found out omega as function of r, like we will be interested in for what value of r omega will be equal to 0. So like we are looking for some layer of liquid which will not be rotating at all. And the fourth thing which we are looking to find out is a rate of heat generation, a rate of heat generation, because see, dissipative forces are doing work inside this system, so that is gonna be negative, and that negative work done by those dissipative forces gonna appear in form of heat. So these all things we are required to find out. So in order to solve this question, please be advised that in this type of situation, viscous force per unit area is given by this expression, that is eta, and velocity gradient will have an expression like r d omega by dr. Please be advised that in this type of situation, viscous force per unit area would be eta into r into d omega by dr. Okay, where like for example, you can imagine a thin layer of liquid which is at distance r from the center or axis, and its thickness obviously is dr. Okay, so the force experience, the tangential force per unit area, is given by this expression over here. So now we are ready to solve this question. Okay, so in the first part we are required to find out, the torque. Okay, so the torque, you must realize, let's draw it here also. So now you must realize this layer of the liquid, okay, let's say is moving with angular velocity omega. Okay, so this layer of the liquid would be some omega plus d omega. Okay, moving with angular velocity omega plus d omega. And now you must realize this d omega is gonna be positive, because as we move away from the axis, you are seeing that the omega is increasing. Like here, the value of omega, the in the direction we have chosen to be positive, is minus omega naught, and this is plus omega naught. So definitely omega is increasing radially outward. Okay, so that being said, the direction of torque each layer will experiencing like due to the adjacent liquid, so this would be the direction of torque. Torque, you understand, is opposite of direction of d omega by dr. One negative sign also we must be putting over here. Okay, so this is torque. And next, like this would be nothing but tau plus d tau, and you must realize again that tau is gonna be constant. Okay, tau is gonna be constant, and that is what is going to help us in finding out the magnitude of this torque. So when we will be writing this magnitude over here, okay, so this tau will be equal to the magnitude which we are writing would be simply equal to eta, okay, into area we will be writing. So the area again would be 2 pi r into L. Okay. And using this expression, r d omega by dr would be the velocity gradient. And this is the tangential force. You realize the tangential force would be acting in this direction everywhere tangentially, and this would be, when multiplied with the arm, it will give us the torque. So this is basically d tau. Okay. Or simply this is okay, this is the expression for torque on this one. So this is total torque over here. We do not need to write this. This is torque here. Okay. And now we want to find out the value of this torque. Knowing that this torque here is a constant. Okay. So we can rearrange this differential equation. Okay. And this would be d omega. Okay. And that would be tau divided by 2 pi eta L. Okay. And that will become dr by r cube over here. And we can integrate both side. This term is constant clearly. Okay. And we must realize at r is equal to capital R, the value of omega is nothing but minus omega naught, and r is equal to 2r, the value of omega is nothing but plus omega naught over here. So solving this, we are getting the left hand side will turn out to be 2 omega naught, and the right hand side would be tau divided by 2 pi eta L, and that would be, like, for example, 1 by 2r square minus 1 by 2r square would be the integration. Okay, so let's change the limit from 2r to r. It would be taking care of that negative sign and solving for everything now. Like here, the tau we will be getting here is replacing all the values. 32 by 3, that would be pi eta L r square omega naught. So that is the expression for torque which all the layers would be experiencing. Okay, and I hope you understand. Like, you need to apply, let me use some different color pen on this diagram here only. Say this color. Okay, so you understand, like, this is how, if we think of an layer which is adjacent to the inner cylinder over here, so the cylinder will be exerting a torque in this direction, so this will be exerting, the liquid layer will be exerting torque in this direction. So external torque we need to apply, that would be in the direction of omega naught here, and similarly external torque we need to apply, that would be in the direction of omega naught in the inner and outermost cylinder as well, and the magnitude of this would be same as this tau external. Okay, which we have already found out for the answer for the first part. And now we are required to find out the angular velocity as function of time. So in order to find out the angular velocity as function of time, we are going to use same differential equation, and one limit we already know, the value of torque we already know. Upper limit we will be taking as omega at r. Okay, so this differential equation will turn out to be d omega, and when we will be substituting the value of tau, which we have got it from here, that will turn out to be 16 by 3 r square omega naught into dr by r cube. Okay, and we need to integrate it with appropriate limits, so that will be at capital R we have velocity as minus omega naught, and at small r we are willing to find out this omega. So solving this, it will give us, like, the left hand side will become omega plus omega naught, and that will be equal to 8 by 3 r square omega naught into 1 by capital R square minus 1 by r square over here. So this is what we will be getting. Okay, so now so the value of omega, by rearranging this, what we will be getting over here is nothing but omega by 3 we can take common, and that would be 8r square by r square minus 5 over here. So this is the value of omega as function of r, okay, that we have got. And in order to answer for the third part, we were looking for the value of r such that omega is equal to 0. We can clearly see that 8r square by r square is nothing but uh, equal to 5 over here. So that gives us r is equal to root 8 by 5 times capital R. So that is the answer for the third part. And now answer for the fourth part that is being asked here is the rate of heat generation. Rate of heat generation, you must realize, that is power dissipated would be in magnitude, like in absolute value, that will be work done by external agent. Whatever is the work done by external agent, okay, negative of same work done would be done by viscous force, and that much amount of heat would be dissipated, okay. So like you can say that that would be negative of that, okay, because P external here, like dissipated heat basically is negative over here. So now let's look into the diagram, okay, again. So here you can see, so this external torque, okay, is due to this external torque, the outer cylinder is rotating with angular velocity omega naught, and the angle between tau external and omega naught is equal to 0 degrees. So they are in same direction, and here they are in same direction as well, okay. So you must realize, when we are trying to find out the work done by external agent, okay, so the work done by the torque on the inner cylinder would be simply like tau dot omega. Rate of work done is basically tau dot omega. So this would be simply tau omega naught on the inner cylinder, and tau external, also you can say tau external into omega naught on the outer cylinder. So this turns out to be minus 2 tau external into omega naught, and tau external's magnitude is same as tau, which we have found out in the previous part also. So this comes out to be minus 2, and the torque here is nothing but, which we have found out, is 32 by 3 pi eta L r square omega naught into omega naught. So that is equal to omega naught square. So that is answer for the fourth part. So we have solved this question, okay. Okay, so here up till now, here we have discussed some problems of linear velocity profile and some problems of non-linear velocity profile we have also looked. So I think that much is enough for the revision purpose. There are other problems based on these types of velocity profiles, and that you must be definitely be practicing on your own. So have a good luck, okay, in doing all those problems, okay. So now it's time for us to now discuss about the Stokes law. Stokes law. So there was famous scientist named Stoke, okay, and his observation was that when a solid body moves inside a fluid, or you can say moves inside a viscous fluid, it experiences a drag force, okay, due to the presence of that viscous fluid, and the direction of that force is opposite of the velocity, instantaneous velocity, and its magnitude is directly proportional to its velocity, okay. And a very simplified form of this equation, that is for a spherical body, let's say we have a you can say, for a spherical body, okay, and let's say the radius of this is r. So if this is moving with certain velocity v in this direction, okay, it will be experiencing a drag force due to the viscous liquid present all around it, okay. So if this is its velocity, so the direction of drag force will be opposite, and let's say viscosity of surrounding liquid is eta. So this, the expression for drag force will be simply given by, that would be minus 6 pi eta RV, where V is the instantaneous velocity and this Fd is the viscous force or drag force, you can say. Eta obviously is the coefficient of viscosity for the surrounding liquid, and R is the radius of this sphere. Okay, so we will be restricting our discussion for a spherical body only. So that will be given by this expression. So once we have got that, like one interesting problem we want to figure out, the problem simply is, let's say there is a spherical body, okay, of, let's say, density, or rho s is its density, and let's say r is its radius over here, okay, and the surrounding liquid or fluid, you can say, has density rho l, okay, and its viscosity is nothing but eta. So these are the parameters given, and let's say it has been projected with certain velocity v naught. Let's say initially at t is equal to 0, its velocity v is equal to v naught over here. Okay, so now you must realize it would be experiencing what all forces over here. So try to figure out. Okay, so first of all, it would be experiencing its weight. Okay, it will be experiencing buoyancy as well, okay, because it is inside a fluid. And apart from that, we have just studied about the Stokes law. Okay, it will be experiencing a drag which would be in opposite direction, Fd. The magnitude of these all forces, collectively, W minus B, that W effective we can write down, that is nothing but W minus B, and that you understand is nothing but W into 1 minus rho L by rho S over here. And when you will be substituting the value, that is nothing but M times G, and M would be nothing but rho S into 4 by 3 pi r cube into G. Okay, so into 1 minus rho L by rho S. So rearranging this, you will be getting 4 by 3 pi r cube into, or you can say, um, rho S minus rho L times G. So that is the effective weight we have already got. Okay, or we can also term it as you can say M times G effective. G effective, you understand. So let's term it as M times G effective over here for time being. And the drag force, which we already know, this drag force is nothing but its magnitude is 6 pi eta r v. For a given r, like this thing would be constant. So let's say this constant is k. So that is k times v. For just for simplicity, we will be writing. So once we have done this, the equation of force, first we want to find out the velocity as function of time. So first thing we want to find out is velocity as function of time. So for that, we need to write the equation of force, okay, in, let's say, vertically downward direction. So that got to be m times dv by dt, mass times acceleration, is equal to net force. So that would be m times g effective minus k times v. So that is our differential equation which we are looking at. So when we will be rearranging this differential equation, this will turn out to be dv divided by mg effective minus kv is equal to, say, dt by m over here. And when we will be integrating both sides with appropriate limits, so you must understand the initial condition which we have already given here. At t is equal to 0, v is equal to v naught, and at t is equal to t, we wish to find out this v over here. Okay, so solving this differential equation will simply give us like v is equal to v naught into e to the power minus kt by m plus vt into 1 minus e to the power minus kt by m over here. Where now look at this term over here, this vt, which is also known as terminal velocity. Like vt's expression would be nothing but you must realize this quantity divided by this quantity over here. So that is mg effective divided by k. And let's substitute all the values. Mg effective we substituted for 4 by 3 pi r cube into g into rho s minus rho l, and the value of k we substituted for, that was 6 pi eta times r. Okay, so rearranging that expression, we are getting 2 by 9 r square g by eta into rho s minus rho l. So now let me rewrite that expression. Like vt is equal to 2 by 9 r square g by eta into rho s minus rho l, and this is some expression you must remember, because this is the expression for terminal velocity. Okay, we will be looking more closely into this concept of terminal velocity, but right now here we have got the velocity as function of time. So my next motive is to get me the acceleration as function of time also, because the force on that moving body is varying, because drag force is a function of velocity, so it is experiencing a variable force, so the acceleration would be variable as well. So the second thing I want to get is acceleration as function of time. So acceleration obviously is dv by dt, and just looking in this above relationship, this dv by dt is nothing but mg effective minus kv by m. So this quantity is nothing but g effective minus k by m times v, and v as a function of time we have already got. So let's substitute that value. So that would be g effective minus k by m times v naught into e to the power minus kt by m plus vt into 1 minus e to the power minus kt by m over here. So like solving this, we will be getting like ge minus, you can say k by m into v naught into e to the power minus kt by m. And now you must realize this multiplied with this quantity like vt. Okay, k times vt is nothing but you can say like already looking at this expression, k times vt over here is nothing but mg effective. So when we will be dividing with m, so this term we will be getting is simply minus ge, or minus minus it will become uh, or simply let's for instance write ge into 1 minus e to the power minus kt by m. Basically k by m into vt we have substituted as g using ge using this relationship over here. So now you must realize that this term and this term here will be cancelling over here. So what I will be ultimately getting is nothing but ge minus k v naught by m into e to the power minus kt by m. So you can see like this would be the initial value of acceleration you can see, and here the acceleration is a exponentially decreasing function. So we here are able to write not only velocity but acceleration as function of time as well. Okay, so let's now, with the help of these expressions, let's look into different cases. And the first case is the most simplest one, the case one, when v naught is equal to 0, means the body is not projected, simply dropped from some height. Okay, so in that case the velocities expression will simply become vt into 1 minus e to the power minus kt by m. Okay, and the acceleration term will simply become ge, or effective g, into e to the power minus kt by m over here. So when you will be drawing the graph of these two functions, for example v versus t graph, if you draw, okay, so you can clearly see that at t is equal to 0, looking in this relationship, at t is equal to 0, you can clearly see that v is equal to 0, and at t tending to infinity, okay, you can see v is tending to vt over here. Okay, so like this would be the, you can say, saturation value, and the graph will look something like this, and this is the terminal velocity. So after a very long time, this body will be moving with terminal velocity, and you should realize the A versus T graph also, A versus T graph. So for A versus T graph, the initial acceleration you can see, that is nothing but GE, which is exponentially decreasing. So after a very long time, the acceleration will become 0. So that is the idea. After a very long time, okay, the acceleration will become 0. That means the net force acting on that the body will become 0. So it will continue to move with that constant velocity, and that velocity here is known as terminal velocity, the expression for which we have already looked into. So this is the simplest case we had. Now let's look into the next case. Let's say case 2, where we have, let's say, if v naught is positive, means the body is projected vertically downward. So here in this situation, okay, the v will be equal to v naught into e to the power minus kt by m plus vt into 1 minus e to the power minus kt by m. Already we have looked into this relationship, and let's further investigate that. So you must realize at t is equal to 0, v is simply equal to v naught, and t tending to infinity, basically v is tending to vt. Okay, so the graph of v versus t will look like this. Let me tell you, the graph of v versus t will look like this. So this would be the saturation value, I must say. So this is obviously the terminal velocity, and now this v naught, like we can divide it into further two special cases. If this v naught is less than vt, so the initial velocity, if it is less than vt, like for example, if v naught is less than vt over here, so then this graph will start from here and ultimately reach its terminal value. And if v naught is greater than vt, so its value, initial value, would be somewhere over here. So the graph will look something like this, you must realize. Okay, so with whatever velocity is projected initially, okay, in downward direction, you can say it can be greater than or less than also from the terminal velocity. So if it is greater than terminal velocity, so initially it would be experiencing a downward drag. Okay, so that will decrease its speed, and ultimately its speed will reach to the terminal value. And same in the case of when velocity is smaller than terminal velocity, so its speed will continue to increase and reach a terminal value. And now if we look into the acceleration versus time graph over here, the acceleration versus time graph. So let's say this is acceleration versus time graph over here. So in these two special cases, like let's write the expression for acceleration first. So acceleration is basically ge minus k v naught by m into e to the power minus kt by m. So you must realize that at t is equal to 0, the value of acceleration is nothing but ge minus kv naught by m, and obviously at t tending to infinity, the value of a will be tending to 0 over here. And depending upon whether the value of v naught is greater or less than vt, depending upon that, like the acceleration, initial acceleration would be either positive or negative. Means positive acceleration simply means that the acceleration is in the direction of velocity, so speed is increasing. And negative acceleration means the direction of acceleration is opposite of velocity, means speed is decreasing. So the first case, if vt is smaller than or v naught is greater than vt, let me use different color pen. So the first case is if v naught is greater than vt, so this quantity will turn out negative. So it, like the initial acceleration value ge minus kv naught by m, which is negative, will lie somewhere here. Okay, and this will be having this graph. Final acceleration, you can see in both the cases, is gonna be equal to 0. And if v naught is less than vt, you should realize the initial acceleration would be something positive. So ge minus kv naught by m here is positive. Okay, so like the acceleration graph will look something like this over here. And now let's quickly investigate the last case here, okay, which says case 3. The way we have written our equation in that, if v naught is negative, means the body is projected vertically upward. So if the body is projected vertically upward, you must realize initially it will be experiencing a downward drag. Okay, it will be experiencing a downward drag, means okay, its speed will decrease. It will at some instant it will become 0, and then it will continue to rise in downward direction until the velocity achieves its terminal value. So the graph here will be looking something like this. Same expression for velocity would be there, only the value of v naught would be negative. This is the terminal value vt, and the initial velocity here is negative somewhere here. So what will happen, its speed will first decrease, and at some time its value will become 0, and then it will continue to then increase, and it will be having a terminal value at vt. So this is v versus t graph. And secondly, if we draw acceleration versus time graph, so you must realize, like the initial acceleration, which we know g effective minus kv naught by m. So now you realize this term is basically negative. So the value of this term ge minus kv naught by m is something greater than g, you must realize. So its acceleration would be greater than the effective gravitational acceleration over here. And but like it will start decreasing, and after a long time, the net force acting on the body will become equal to 0 when the velocity will reach its terminal value, and its acceleration will become 0 as well. So that is one of the idea. That was case 3. One another important aspect of this problem is, so once this body has achieved its terminal velocity, okay, it continue to move with terminal velocity, and we wish to find out rate of heat generation. And you must realize rate of heat generation would be nothing but, or dH by dt would be nothing but, that would be negative of rate of work done by viscous force or drag force, which is, you see, is non-conservative in nature. So that is rate of work done by viscous force. So that, I think, is very, very simple, because the formula which we'll be using, that would be force dot velocity. So that is drag force dot velocity. And here um, we are looking at the terminal velocity over here. So this is going to be obviously drag force and the terminal velocity, they are oppositely directed. So this dot product would be negative, and negative negative will become positive. So this will give us, that would be 6 pi eta r into Vt square over here. So now you must look more closely over here, because we already know the expression for Vt. So let's substitute that value. So 6 pi eta r, and the expression for terminal velocity was nothing but 2 by 9 r square g by eta over here, okay, into rho s minus rho l square. Like this is Vt square term. So now you should realize the important thing, like this thing is important for mains over here, like simple formula based question might be asked. So but here you should realize this dh by dt. Now you see r square square, so that becomes r to the power 4. So this, and that multiplied with r, so this dh by dt is directly proportional to r to the power 5. So this is one another important relationship which is specifically useful for mains, JEE mains over here. So now let's move on to the next concept. The next concept I am going to talk about is about Reynolds number. Reynolds number. Okay, so Reynolds was a scientist um, who devised a method to find out using the flow parameters that whether the flow is laminar or turbulent. Okay, so Reynolds number is defined as rho Vd by eta. Okay, and you must realize that this is nothing but a dimensionless physical quantity. There is no dimension, you can check for it. Okay, so basically rho, you must realize, is nothing but let me write over here, rho is the density of fluid, okay, and v is the flow velocity. D is something called hydraulic diameter, and eta here is viscosity or coefficient of viscosity of fluid. And for a special case over here, you can see, like for a flow of fluid in a pipe, this hydraulic diameter would be same as the diameter of this pipe over here. So this is D, and let's say liquid is flowing in this direction and the flow velocity is V. Okay, and it's the parameter for the liquid is its density is rho and viscosity is eta. So depending upon these terms, we will be able to find out its Reynolds number. So what is the use of a Reynolds number? So that is basically to find out the pattern of flow. So the information, let me give you the information. If Reynolds number for a given flow inside a pipe, if it turns out to be less than 1000, then you can definitely say for sure that flow is laminar. Flow is laminar, and if it turns out to be greater than 2000, so then you will be able to say that the flow is turbulent. Okay, and it will no longer be a streamlined flow. And turbulent flow, you can see, like for example, if this is pipe, okay, and the liquid is flowing in it, so laminar flow was basically layered flow. The flow was in a, like liquid were flowing in different layers, okay, and that was steady state flow and no layer were mixing with each other. And now this is for laminar. And in turbulent flow, what happens, the layer of liquid mixes with each other, something like this. Okay, so here like localized eddy currents are formed over here. So like this is not good for like the piping system over here, because here you see when the fluid is flowing in laminar flow, here you can see it is not exerting any perpendicular force on the wall of this pipe, you can clearly see. But here when it is like having eddy current, and the component of flow velocity will be having a direction perpendicular to the surface of pipe, so here it would be exerting normal force on that pipe as well, so that might damage this pipe also. So for a normal pipeline design, basically the flow engineers try to keep the flow laminar. They try to avoid the turbulent flow in order for the long life of the pipe. Okay, so but there is another trade-off over here. So in order to have laminar flow, Reynolds number needs to be less. Okay, Reynolds number need to be less. So that means the flow velocity v, now look in this expression, the flow velocity v has to be less as well. So if flow velocity v is less, the volumetric flow rate, as you know, q is equal to a times v, will also become less. So like the piping system will be able to handle less volumetric flow rate. So there is a trade-off between the volumetric flow rate. If you want to increase the volumetric flow rate, you have to install the stronger piping system, and if you can manage with less volumetric flow rate, like less strength of the piping system can also do the work. So there is basically it's an engineer job to optimize between these two criteria. Okay, and obviously you might be wondering over here, like if Reynolds number turns out to be less than 1000 and greater Reynolds number is greater than 1000 and less than 2000, so what would be the nature of flow? So let me tell you here, flow nature will be unpredictable. Unpredictable means, that means like somewhere at some localized point the flow would be laminar, and another places the flow would be turbulent, and those pattern would be varying with respect to time. Like for example, at one place right now we are having laminar flow, at the later instant we will be having turbulent flow. So that would be very unpredictable nature of fluid flow, and that basically would be a nightmare for a fluid engineer. Okay, because okay, so if he knows that the flow is laminar, he can design the system appropriately. If he knows it is turbulent, he can design his system, okay, in order to tolerate the turbulent flow as well. But if he is unable to predict the nature of flow, then he cannot utilize any design parameter. Okay, so that is why that is very difficult to operate if the Reynolds number lies between 1000 to 2000. Please be advised about that. And one more thing I would like to add over here, the just looking at the Reynolds number a different way, let me tell you about physical significance of Reynolds number. The physical significance of Reynolds number, as we have already stated, that the Reynolds number is given by the expression rho Vd by eta over here, and this term I would like to rearrange it like something like this. So rho V square into A in the numerator, and in the denominator I would write eta AV by d over here. So now please try to look into this, like this expression and this expression are essentially same, but we have rearranged it in this form because see, in the numerator what you are seeing, that rho v square a, this term you must remember, that is the thrust force exerted by the incoming liquid or outgoing liquid. So basically what you can say, that is nothing but inertial force of moving fluid, you can say. And you should also, like we have just learned about this expression, that is nothing but the viscous force. So that is nothing but the viscous force of moving fluid. Okay, so basically you must have realized that Reynolds number is nothing but gives a ratio of the inertial forces upon the viscous force. Means if inertial forces are high, okay, means Reynolds number would be more. Okay, or you can say if viscous forces is low, Reynolds number would be high over there. Okay, so like that is a measure of whether like the inertial forces are more or viscous forces are more. So and depending upon that, we can predict the nature of flow over here. So this is basically the criteria of Reynolds number. One another aspect of this problem, you must realize there is something called critical velocity. The concept of the critical velocity. So you have already got the Reynolds number, and from that, if Reynolds number is given and another design parameter are given, you will be able to find out the value of V. And if V is less than critical velocity, you can simply say flow will be laminar. Flow will be laminar. And if you must realize, if V is greater than that critical velocity, flow will be, you can say, turbulent. Okay, and this critical velocity, you can find out if the critical value of Reynolds number, if you substitute in some designing parameter, you will be getting the value of this critical velocity. So here our time is up. Okay, so that's it for today. Thank you very much. Thank you very much for joining